2.5, rates O change, and particle motion part 1. We're going to look at particle motion again once we learn about the integral. But this is all going to be about applications of the derivative, because after all, the derivative does give us the rate of change of a function, right? What type? The instantaneous rate of change. Well, we can still talk about average rates of change, which would require not calculus, but algebra. It's still pretty good to know some of that stuff. All right, so if f of x represents a quantity, then f prime or df dx in Leibniz notation represents the instantaneous rate of change. And we could be talking about then the rates of change of any quantity that we're measuring. One of the most useful applications in terms of physics, and as far as Newton was concerned, was how fast position changes, which would be particle motion or velocity, instantaneous acceleration. But you can talk about how fast anything's changing. You just don't usually describe it as velocity, right? Man, it's warming up outside pretty quickly. The temperature's velocity is a big positive number. That doesn't really make sense, right? But it's the same idea. So what we're going to do first off, on example 1, is we're going to learn how to take English sentences or take mathematical sentences and transcribe them into English sentences. Because one of the things we're going to have to do for a lot of these problems is interpret our answer with a complete sentence. So we'll be talking about the rates of change of all kinds of things. Like on example 1, temperature. And because it's October 5th and fall is upon us, it's a pretty apropos subject matter in this question here. The temperature T in degrees Fahrenheit of a cold yam placed in a hot oven is given by this. Big T, the temperature, is a function of little t, where little t is going to be the number of minutes since the yam was put in the oven. So we have two letters, but they're really the same. Capital T is the temperature in degrees Fahrenheit. Little t is minutes that the yam has been in the oven. Cold yam, hot oven. In a complete sentence with units, translate the practical meaning of the equation f of 20 equals 255. Well, here's what I would recommend doing. When you're talking about applications, it's probably nice to just maybe label an x and a y axis. And on the y-axis, we're measuring big T in degrees Fahrenheit. And on the x-axis, we're measuring, or t-axis in this case, we're going to be measuring time in minutes. So now you can just reference that, and you have your variables listed, and you have their units as well. So the independent variable is minutes, and the dependent variable is Fahrenheit. Now this is an instantaneous quantity, right? F of 20. That means what is F at 20? So it is instantaneous, but it's not an instantaneous rate of change. It's the instantaneous temperature, which we can measure. So how would you start off a sentence? I want you to get in the habit of starting with an introductory adverbial clause that references the moment in time. So, at T equals 20, is that minutes or 20 degrees Fahrenheit? 20 minutes. So at T equals 20 minutes. That's the safest way to do it. You can refine that a little bit, saying after the cold yam has been in the oven for 20 minutes, comma. You could do that. That's just a little bit wordy. At T equals 20 minutes, comma. And what is 255? What are the units of 255? Degrees Fahrenheit. That's the instantaneous temperature of the yam, right? So at T equals 20 minutes, comma, the yam's temperature. You don't want to use the passive voice, right, and say the temperature of the yam. The temperature belongs to the yam, right? The yam's temperature is 255 degrees Fahrenheit. It's just wimpy. It's weak, right? It's not assertive writing. That's all. Now, sometimes when you use the passive voice, it's okay if you're trying to imply that the person possesses humility and modesty, right? Right? The humility and modesty was possessed by that individual. He didn't. He owned it, but he didn't want to own it. No? Okay. This is the yam's temperature, man. It don't belong to anybody else. Yam's temperature. It's also a little more economical. It requires fewer words. Okay. Does that require calculus at all? No, it didn't. Okay, let's move on to the next one. What is the sign of f prime of t? Why? Well, f prime is going to be the derivative, right? So here's what I would do. F prime is the same as big T prime. And what are the units of the derivative? It is the units of slope, right? So it should be units of y over the units of x. So it should be degrees Fahrenheit per minute. That's another nice thing to label right there in the first quadrant. So anytime you talk about the rate of change, you're talking about the units of degrees Fahrenheit per minute. So what is the sign of F prime? It's positive. The next follow-up question is why? Why is it positive, Rap? Yeah, very good. It was a cold yam in a hot oven, right? It wasn't a hot yam in a cold oven. So if you want to kind of think about it, there's the initial temperature of the yam when we put it in. The temperature should increase, right? If the oven's hotter than the yam, how should it increase? Should it increase at an increasing rate? Should it increase at a constant rate? Or should it increase at a decreasing rate? Should it increase at a constant rate? Okay, if it increases at a constant rate, that would be like that. And then when would it stop? Never. That is one heck of an oven. Right? It'll never stop. If it increases at an increasing rate, that's also going to, the temperature, I wouldn't want to handle that even with oven mitts, you know. It should increase at a decreasing rate, yeah? And it should be approaching some upper bound temperature, which should be what? The oven's temperature, right. So that's a little bit more reasonable. And I think it's the law of like enthalpy maybe or something like that. Something to do with specific heat. Like the closer it is to the actual temperature, the slower it's going to gain heat because it already has absorbed so much or something like that. I'm not sure. That's a different class. But it's reasonable to think that its temperature is going to increase at a decreasing rate approaching the oven's temperature. But at either rate, the temperature is increasing, right? And so the derivative sign should be positive. So let's answer. What is the sign of F prime T? Positive. Comma, since, what'd you say, Rap?
No longer the yams in the oven higher.
Yes, the yam's temperature is increasing. How about that? Is that a nice paraphrasing of what you said, kind of? Yeah, yeah. Because what we're measuring on the y-axis is getting bigger, essentially. We're measuring temperature, and it's getting bigger, so it's increasing. What are the units of F prime of 20? I think we've already done that. The units of F prime are the units of slope, which are degrees Fahrenheit per minute. All right, so now it's all leading up to this. In a complete sentence with units, what is the practical meaning of the statement F prime of 20 equals 2? 20 is your independent variable. What are the units of 20? Minutes. So that's your introductory adverbial clause. So at t equals 20 minutes, which is a lot shorter than saying after the yam has been in the oven for 20 minutes. This works as well. At t equals 20 minutes, comma, what are the units of 2? Degrees Fahrenheit per minute. So that's an instantaneous rate of change of the yam's what? Temperature. So at t equals 20 minutes, comma, the yam's temperature is, what do we say? Is 2 degrees Fahrenheit per minute? Increasing. Very good. Here's the thing in the English sentence. When you're writing it from a math sentence, you want to interpret the rate of change as increasing if it's positive or decreasing if it's negative. You don't want to just say changing because that's generic. We want to say increasing or decreasing. The yam's temperature is increasing. You could say at a rate of, but that's a lot of words too. So just say by 2 degrees Fahrenheit. And usually in the sentence we write out the word per, P-E-R, not P-U-R-R-R-R-R-R-R, because that one's hard to stop. Per minute. Instead of just putting like the slash diagonal. 2 degrees Fahrenheit per minute. We have the story of the yam at 20 minutes, don't we? We can actually write like a short little children's book now, right? It would be like 2 pages long. At t equals 20 minutes, the temperature of the yam is currently 255 degrees. And turn the page. And increasing by 2 degrees Fahrenheit per minute. The end. The story of the cold yam. What? Oh, that could be like the sequel. We want them to buy more books. So maybe in the sequel we eat the yam. We probably have to let it cool off first, right? So that could be like the middle book. Right? Take the yam out of the oven, let it cool off. Wait. And then book 3, like, eat the yam. Okay? And that one can involve grandma and grandpa because they're probably over for dinner. That'd be a longer book. Yeah, we could split that. We could split that last book up like they did with the Harry Potter thing. We could probably split that one up into like 2 different movies. The eating of the yam. All right. So anyway, that's great. That tells the story of the yam at t equals 20 minutes. Now, if you had to predict the temperature of the yam at the 21st minute mark, if you had to predict, what would you predict? This could be like advanced book, like one of those thought-provoking questions at the end. If you had to predict what the temperature of the yam would be at the very next minute, at the 21st minute, what would it be? What? 257. How'd you come up with that? It's increasing. The temperature is increasing by 2 degrees Fahrenheit per minute. And if I let 1 minute elapse, it's reasonable to think that it would be around 257, right? You just add 2 to that. Now, is it actually going to be 257 degrees based upon our diagram? No, it should be a little bit what than 257? Less than. It's because our tangent line, if we drew it at 20 right up here, what we just did is we're using a tangent line at 20 to approximate the temperature in the future. This is called extrapolating. If I looked at the 21st minute, this would be the value that I just calculated, and here would be the actual value. Because the tangent line is above the curve, we know that 257 is an approximation of the temperature in the next minute, but it's a little bit more. This is what you call marginal prediction. In economics, when you have marginal profit, marginal cost, that's what marginal is. Use the rate at the current level to forecast what would happen 1 more unit in the future. So already you can see kind of a nice little application of knowing the rate of change in an instant. Good to know. All right. Note. Yeah, okay, y'all can read that. Example 2. Let's go from cold yams to ice cream. I don't know. That would be awesome to have yam-flavored ice cream. I was just thinking that. Because, like, if you go to the store, like nowadays, like almost everything is pumpkin-flavored. You can get pumpkin-flavored anything. Why not yams, though? Let's read on. An ice cream company knows. The ice cream company knows. That's kind of what's creepy about ice cream companies is they know. They know that the cost, C, in dollars, to produce Q quarts of cookie dough ice cream, they know that it's a function, in part, of the number of quarts they produce, right? The more quarts they produce, the more it costs them to produce it. That makes sense, right? Yeah, now there might be some economies of scale, right? The more they produce, the less it is. But there might be what we call a point of diminishing marginal returns where it might cost them more beyond a certain point. That's all economic forecasting. But all we do know is from the basic standpoint of what we're doing, the more quarts they produce, the more it costs them to produce it, right? So C, the total cost, is a function of Q, quarts. Let's go ahead and draw a little picture here. First quadrant. We have Q, which is our independent variable, and that's going to be our quarts of ice cream. And we're measuring the cost here. So we measure cost in dollars, cents, or in dinar? Yeah, in yen. Let's do dollars. Okay. Oh, that's a good question. Where is it located? It tells. Oh, darn. Okay. I don't want to have to convert. All right. So if 200 equals 70, explain in a full sentence what this mathematical sentence is telling us in the context of the problem. F of 200 is 70. So 200, what are the units of 200? Quarts. So that's quarts, and 70 would be dollars. That's an instantaneous rate of change? No? It's an instantaneous position, right? It's analogous to the position. What is the quantity at that moment? So, how about at the 200 quart production level? You could say that, or you could say when 200 quarts of ice cream are produced, right? At the 200 quart production level, comma, what? Yeah, good. The cost of production is $70. Could you do something similar like the cost of producing 200 quarts is $70? Yeah, it works as well. Yeah, you can always refine this. You know, being maybe like a wordsmith, you could always contain the idea in a much more efficient sentence. But the way that I'm writing it every time is always going to be the same. I'm always going to have that formula for addressing the moment in time, or what will later be the interval of time, with units, and then talking about what the value is with units or how fast it's changing at units. And why do I do that every time? Because this is not an English test. You're not going to get points for sentence structure, sophistication. You're going to get points for having all the essential elements, which are you have to reference the moment in time with units, and you have to say what the quantity is or how it's changing with units. So if we get in the habit of doing it like this every time, you can go home and refine the words, on your own. But sometimes if you refine it too much, you might lose something. So yeah, what did you say the refined sentence would be? One more time.
The cost of producing 200 quarts is $70.
Very good. The cost of producing 200 quarts of ice cream is $70. That contains everything as well. Good. Part B, if f prime of 200 is 3, explain in a full sentence what that's telling us. So let's come back over here real quick. What were the units of f prime, which is really c prime as well? What are the units? Units of slope are always going to be units of division, right? Units of y over units of x. So it'd be dollars per quart, dollars per quart. The units of slope are dollars per quart. So we could say again 200. So at the 200 quart production level, and that's what I'm going to always start with. The cost of production, that's what we're measuring on the y-axis. What'd you say is what? Increasing or decreasing? Is increasing. Good. Good. By $3, and we'll spell it out here, by $3 per quart. Again, when you're writing your sentence, you usually spell it out. So there's a difference between a numeric answer and a verbal answer. A numeric answer can be negative. We haven't seen one yet that has a negative rate, but your verbal answer would then interpret the negative sign as decreasing. All right, so if this was your company and it was costing you $3 more per quart to produce the next one, would you produce that 201st quart? If it's going to cost you an additional $3 to produce it? Well, there's a lot that depends on that, right? You need to look at, okay, if it's going to cost me only $3 to make the next quart, but I can sell it for an additional $10, there's still profit there. So are you trying to maximize profits, or are you just trying to make a profit? Because there is an optimal profit production level as well. And beyond that optimal level, you still might be making a profit, but less and less. And so all things considered, if it's going to disgruntle your employees by having them work longer hours, is it really worth to squeeze that extra dollar out of them, just to make another dollar? I mean, there's a lot that goes into that. Ethics, not just cost analysis. All right, so part C, if f double prime of 200 is negative 0.1, explain in a full sentence with units what that means. F double prime, what the heck? F double prime is talking about the rate of change of which function? F prime. So that's the slope of f prime. So let's go ahead and get the units of f double prime. The units of f double prime are going to be the units of f prime divided by the units of the independent variable. Like if we were to graph f prime, we would have dollars per quart on the y-axis. That would be like the velocity, right? Velocity, like meters per second against quarts. So the units are going to be dollars per quart per what? Per quart, or per quart squared. Yeah, that's essentially the acceleration. That's essentially the acceleration. So let's go ahead and try it. At the 200 quart production level, we still start with that. Would you all agree? Because it's still the same independent variable. At the 200 quart production level. Now, what does f double prime measure the change of? It measures the rate of change of f prime. What would you call f prime? The rate of change of the cost? So the rate of change of the cost, the rate of change of the cost is what? Increasing or decreasing? Is decreasing by, and then 0.1. Now we say decreasing, that interprets the negative sign, so it's decreasing by 0.1. And now I need units. What are the units of f double prime? Well, it's dollars per quart. Now here you don't want to say dollars per quart squared. Yeah, per quart. Or maybe even say for each quart. or something to that effect to kind of separate them. The rate of change of the cost is decreasing by basically 10 cents per quart for every additional quart produced. No, that's fine. Yeah, just make sure your units work. And again, that's kind of refining the problem a little bit. $0.1 is 10 cents. So if you say 10 cents, there's nothing wrong with that. So this function, the cost is increasing, but at a decreasing rate, yes? So the curve would look kind of like maybe the radical function. The cost is going up, but at a decreasing rate. Okay, so we just looked at essentially the position, the velocity, and the acceleration, but we weren't talking about motion. We were talking about ice cream. Would this make a good book? I don't know, maybe. For junior Bluebell executives, maybe. I don't know. Is Bluebell back in HEB? I know, let's see, Berkowitz, you're still not back in HEB. Yeah? They have nothing, not even like the homemade vanilla and the Dutch chocolate? No.
They're purposely keeping off the shelf so they can sell all their surplus of HEB brand.
Oh, that HEB's doing. Oh, okay, maybe so.
They're trying to squeeze this for all it's worth. Remember when it used to be American chocolate and not Dutch chocolate?
The Dutch. All right. Example 3. This one's kind of cool. Let F of t be the amount of rain. Amount of rain in inches, so we have units that have fallen since midnight, where t is the time in hours since midnight. So t equals 1 is 1 in the morning, t equals 2 is 2 a.m., so on and so forth. In a complete sentence, interpret the following. Okay, so we got f of 10 equals 3.1. I'm going to go ahead and make my little first quadrant here. We have, let's see, rain in inches against hours. That's going to be our function. F is the inches of rain that have fallen since midnight. F prime, then, I know for sure is going to be what units? Inches per hour. That's the rate of change of rainfall. So let's say we're just measuring rainfall. That's a little bit easier than saying the number of inches that have fallen. We're measuring rainfall. You'll be okay with that? All right, so F of 10 equals 3.1. 10 is going to be what? What's that first sentence? Yeah, you could say either at t equals 10 hours, which is the mathematical way to get full credit. That's like the engineer talking, right? At t equals 10 hours. Of course, you might just say at 10 a.m., which would that be fine as well? Yes, that would be kind of refining the sentence. As long as you reference the independent variable, the time that you're talking about, and the units, you're good. At t equals 10 hours or at 10 a.m., comma, what are the units of 3.1? Inches. So 3.1 inches of rain had fallen. Has fallen, have fallen. Fell. No, has fallen. Has fallen? Have fallen. If it was just 1 inch, 1 inch has fallen. But if it was 1.1, that's more, 1.1 inches have fallen. Okay, whatever. I think have is okay, right? Good. What's part B? Is that F prime? No, that's what? F inverse. How do we get the graph of F inverse? Yeah, we switch the X and Y around. So we are now going to have F inverse here. We have hours measured as a function of the number of inches of rain that have fallen. Wow. Our independent variable now is inches of rain. So like we're home and we have nothing better to do. We are keeping track of our life by just watching the rain gauge. It's the independent variable, right? Yeah, Wapner comes on when there's 2 more inches of rain that have collected. Wapner. That's the Rain Man. That's maybe why they called him the Rain Man. I don't know. Have y'all seen that movie, Rain Man? Yes, it's one of those movies you should see. Yeah, Dustin Hoffman and Tom Cruise, Rain Man. You should see it. It's a good movie. All right, so what are the units on 10? Inches, right? So when 10 inches of rain have fallen at that moment of time, comma, What are the units of 16? Hours. 16 hours, yeah, have passed or elapsed. It's P-A-S-S-E-D, not P-A-S-T. Have passed. Have elapsed, yeah. Keeping track of time by watching the rain gauge. Nice. All right, no big deal with that. Now we're getting to the derivatives. F prime of 8 equals 0.4. What are the units of 8? Hours. We're back to F, so it's still the independent variable. So, again, at 8 a.m., I'm okay with doing that. We don't have to be so bland with our explanations. And that's still units, right? A.m. would be the units at 8 a.m., comma, what are the units of 0.4? It's F prime, so it should be inches per hour. That tells us how the rate of change of the rainfall. Rainfall is, or what? How would you word that? Rain is falling at? That'd be good. Rain is falling at? The rate of rainfall is, yeah, either one of those. The rate of rainfall is 0.4 inches per hour, or rain is falling at a rate of? What would you say it, though? At 8 a.m., I like rain is falling at 0.4 inches per hour. So even though it's falling, that doesn't necessarily mean that that's a negative rate, because we're measuring how much rain we're collecting. So you could say rainfall is changing, or rainfall is the collected rain is increasing. So a lot of different ways you can maybe say that. Rain is accumulating. That's another way to say it, right? Rain is accumulating at 4.4 inches per hour. Well, again, this is a very subtle thing. You don't have to necessarily say it. If we say it's falling, then we know that we're increasing the amount that we're collecting. Let's go back up here and read again. It's the amount of rain that has fallen. Let's do that. Let's when in doubt, go back to specifically what it tells you. So at 8 a.m., comma, the amount of rain that has fallen is increasing by 0.4 inches per hour. Write it out. That would actually be preferred, yeah. Because now you're actually speaking specifically to the quantity, the words that they gave you in the beginning of the sentence. Would it be wrong to say that rain is falling by 0.4 inches per hour? It conveys the exact same thing. If you say the rate is increasing, that would be the second derivative. Yeah, anytime you say rate, you're talking about derivative. Anytime you say the word increasing or decreasing after that, you're talking about another derivative. So that would be the second derivative. All right, here we go. This is F inverse prime. That's how we would write F inverse prime of 5 equals 2. Let's come over here and look at that, units, to get ourselves prepared. F inverse prime, we write it with parentheses. That's going to be units of what? Hours per inch. This would be the guy that keeps track of time by watching the rainfall. He would not have a wristwatch on. He would actually have tied to his wrist a little rain gauge. And when he needed to know what time it was, he would just look at his rain gauge on his wrist. Okay? He's keeping track of how fast time changes by watching how many inches have accumulated. So what would be the units of 5? Well, it's F inverse. Yeah, this is going against our conventional notation here. When 5 inches of rain have fallen, comma, we're measuring the rate of change of time now. So time is increasing? Would you say that? That's kind of weird. How could we maybe come up with a better word? Time is elapsing or passing again? Time is elapsing at 2 hours per inch. Yeah, time is passing at 2 hours per inch. Yeah, okay. Every time we get another inch on our little wrist gauge, it's another 2 hours. Yeah, I guess so. Yeah, and what if it stops raining and time stops? Yeah, I guess. Wow. Wow. We haven't. And it'd be nice to like hope for rain in the future, but how can you get to the future if time's not passing? Oh no, we're stuck in an eternal drought now. Okay, so my point of doing this is to get you to deliberately think, in ways we don't normally think, because you can flip rates. It doesn't really matter. You just have to think about it differently. Like we measure our fuel efficiency in miles per gallon, right? Simply because that ends up being usually an integer greater than 1. If you have a gas guzzler, maybe it's a small integer greater than 1, but you usually get more miles per 1 gallon than you do the other way around. But there is a time where you can measure fuel efficiency not in miles per gallon, but in gallons per mile. And that would be like certain vehicles that it takes more gallons to get 1 mile than the reciprocal, like that thing that used to bring the space shuttle out from the hangar. Like they called it the Creeper or whatever. It was a big thing, and apparently it used 12 gallons per mile to move the space shuttle and the whole launch platform out from the hangar out to the launch site. So that would be a time where you would say 12 gallons per mile instead of a 1/12 of a mile per gallon. Because right, yeah, 12 gallons per mile. Yeah, that's probably the Prius version that they're using. I don't know. Is it a hybrid? I don't know if it's a hybrid. So anyway. All right, so the word instantaneous, we usually don't say what's the instantaneous rate of change at a moment of time. Simply if we just say what is the rate of change at, and we reference a single moment of time, a single time value, a single x value, of course that means at that moment, at that instant. So you're not always going to see the word instantaneous. All right, so here's something that I added, and this is kind of funny. Example 4, an economics example. We already talked about marginal profit, marginal cost. That's using the tangent line slope essentially at a point to predict 1 unit out in the future. In the October 1996 issue of Notices of the American Mathematical Society, that's what AMS is, Hugo Rossi wrote, this is what he wrote, he remembered this or he found this somewhere. In the fall of 1972, President Nixon himself announced that the rate of increase of inflation was decreasing. The rate of increase of inflation was decreasing. Can you hear a president or a candidate saying that? The rate of increase of inflation is decreasing. And you're sitting at home listening going, how's good? Is that good or bad for us as the consumers? I don't know. The rate of okay. So this is what Hugo noticed. He said this was the first time a sitting president used the third derivative to advance his case for re-election. Oh, the first time a sitting president used the third derivative to advance his case for. So part A is to laugh out loud. Do you think Nixon knew what he was? You think he knew it was the third derivative?
No. Was that really the best thing he came up with to advocate for re-election?
Yeah, I don't know, man. I don't know if he was trying to cling to something. Let's see why this is the third derivative. I told y'all that anytime you say the word increasing or decreasing, you're talking about a rate of change, right? So there's one decreasing. Rate of increase, that would be another one. Where's the third one? Inflation itself, right, is a rate of change. It's the rate of change in the purchasing power of a dollar, right? Okay. So the way that something that's changing, inflation, the way that it's increasing, inflation is increasing at a decreasing rate. Is that good for us? Inflation, prices are going up at a rate that is decreasing. Yeah, it's better than the rate of increase of inflation is increasing, I guess. Yeah. I don't think you're ever going to stop inflation. So it has to be increasing, but if we can kind of manage it and taper it off, that's not a bad thing. Did it work? In the fall of 72, did it work? Any presidential historians? Yeah, when was the re-election? When was the election campaign? It was 1976. It would have been 72. And so it worked. Because he resigned in 74-ish, and then Ford took over. Yeah. All right, there you go. Anyone running for homecoming king, queen, still want to just reference the third derivative? All right. Okay, so explain what Nixon meant. We already talked about that. Did we do part A? Okay, cool. So anyway, there you go. You can use that kind of phraseology, not necessarily in a very specific math sense. You can use it almost like as a political technique to obfuscate your point that you're trying to make, right? Okay, winning. I got an A in calculus. Okay, I found that. Yeah, that's cool. I got A in calculus. Yeah. Hey, look, I put this in here. Orwellian twist. Nixon's statement actually allowed for the rate of inflation to increase. So in actuality, his statement was not as indicative of stable prices as it sounds. We know that. Nonetheless, Nixon went on to win the general election over George McGovern with 60.7% of the popular vote. So there you go.
Turn your TVs to channel 4 for the morning announcements, or you can view them on your iPads at nbhstv.com.
All right, we got 10 minutes left. Let's talk about something else that's changing besides temperature, cost of producing ice cream, or the cost to purchase ice cream, right? Inflation. Imagine a sphere. I'll stop right there for a second. Whose radius is decreasing. Oh, not to make y'all panic. If you're thinking about planet Earth, this is a sphere and the radius is decreasing, don't panic, guys. When the diameter of the sphere is 6 feet, so at that moment in time, when the diameter of the sphere is 6 feet with respect to the radius, how fast is the volume of the sphere changing? Explain your result. Okay, so the volume of a sphere. First thing we need to do is figure out what is the equation for the volume of the sphere with respect to its radius. Pi r cubed. Yes. Memorize this. Okay? Memorize this. The volume of a sphere with respect to its radius is 4/3 pi times the radius cubed. Memorize it. This would be our quote-unquote position equation. It tells you for any value of the radius, bless you, it tells you what the instantaneous volume is. Or if you know the volume, plug it in, it gives you the instantaneous size of the radius. We want to know how fast is the sphere changing when the diameter is 6. Now the diameter is equal to 6. That means the radius is what at that moment? 3. So that's our instantaneous moment in time, okay, when it's 3 feet. I want to know how fast the volume is changing when the radius is 3. So guess what I need to do? I need to find V prime of 3. But before I can find V prime of 3, I need to find V prime of R. How do I find V prime of R? Power rule, right? Let's do it. 4/3 pi is a constant, so the derivative of R cubed becomes 3R squared. Times the 4/3 pi, we get 4 pi R squared. That's using the power rule. 3 times 4/3 is 4 pi R squared. 4 pi R squared, by the way, is the what of a sphere? You should memorize this one as well. It's the surface area of the sphere. So the derivative of the volume with respect to the radius is the surface area with respect to the radius. Now that I know V prime R, now I can plug it in. How fast is the volume changing? Exactly the moment when the radius is 3? Well, what's V prime of 3? It's going to be 4 pi times 3 feet squared, which is 36 pi cubic feet. Per what? Foot. If you notice what the units are, 3 is units squared. But if I just put V prime of 3 equals 36 pi square feet, that's the surface area. That's not quite in the context that I wanted. So I'm going to have cubic feet per feet, which of course divides out to give you what? Feet squared. So the sentence would be something to the effect of, at the moment when the radius of the sphere is 3 or the diameter of the sphere is 6, the volume of the sphere is whating? Increasing by 36 pi cubic feet per foot. Okay? So if you divided out the units there, you would kind of lose the context of the rate of change. how fast is the surface area of the sphere changing at that moment? Well, the surface area is going to end up being V double prime of R, yeah? Because if I told you V prime of R is the surface area, V double prime of R would be the rate of change of the surface area, which by the power rule is 8 pi R. That also gives you the acceleration of the volume, doesn't it? The rate of change of the surface area gives you the acceleration of the volume. So now V double prime of 3 is going to be 24 pi. And the units would be, it's the rate of change of volume. So it'd be, there'd be no units except for feet. So that would be cubic feet per foot per foot. Because the units of our previous one were cubic feet per foot, and this is telling us how fast that's changing. So the sentence would be then, when the radius of the volume, or the sphere, when the radius of the sphere is 3 feet, the surface area, actually, maybe if we're talking about it in the context of the surface area, this would be the context of the acceleration of the volume. If we're talking about rate of change of the surface area, we don't need that. We could just say this. Because the units come out to be feet. So we can say now the surface area is what? Increasing by 24 pi square feet per foot. So for every one increase of foot in the radius, or decrease, I guess, because it's getting smaller, we were going to lose 24.
How would the volume be decreased?
Yeah, I need to come back. It wouldn't be increasing. I said that, and I just came back up here. It's decreasing, right? So what would we say? What's that?
Would you just have to interpret that?
No, there should be, well, I don't know. Can we use -3? We would just have to interpret it, yeah. So 36 decreasing by 36 pi cubic feet. You don't want to say the radius is negative. We're going to study something later on called related rates, and we're going to be looking at the rate of change with respect to time, and then we can have negative rates, because we can have something getting bigger. But we don't want to, since we're just plugging in 3, we don't want to let that be a negative. We would almost have to have a negative in our original formula for the volume. So this would be decreasing as well. So we're doing positive calculations, but in the context of the sphere, we know it's getting smaller. So the surface area is actually decreasing by 24 pi square feet per foot. The volume is decreasing by 36 pi cubic feet per foot. And then very quickly here, how fast is the diameter changing? Well, do we know a way to relate the diameter to the radius? The diameter is what? 2r. And so that would be your quote-unquote position equation for the diameter. If you want the derivative, take d prime of r. It's going to be what? 2. And there's nothing to plug into. So you could say, so the diameter is decreasing. Again, we're interpreting it to be decreasing by 2 feet per foot. And again, feet per feet divide out, right, because it's a constant. So the units here get a little bit tricky because we're doing it with respect to another unit of length. With respect to the radius's length, how fast is the volume changing? Later on, we'll do it with respect to time, and you'll get something like feet per second squared, and you get more like acceleration. But this works. So the diameter is getting smaller by 2 feet. For every 1 foot, the radius is getting smaller, which makes sense because it's twice as big. All right, so memorize these, right? The volume of a sphere, 4/3 pi r cubed. Memorize it. The surface area of a sphere is 4 pi r squared. That's the derivative with respect to r. And, of course, the last one here, the shape of a sphere, round. Round. All right, that's a good place to stop for today. Tomorrow we'll have a little quiz, and we'll pick up then where we left off with actual particle motion, which is, it's going to get kind of interesting from here on out. After the quiz tomorrow.